So today we're doing Unit 4, Day 4, Angle Bisectors and Triangles. So we need to remember what an angle bisector is. An angle bisector divides an angle into how many halves? 2. And what kind of halves do you think they should be? Equal. Although by saying halves, that kind of implies 2. 1/2 plus 1/2 is the whole angle. And by saying halves, they're usually halves are equal. All right, but just so we make sure we know this. All right, guys, I need y'all to settle down, please. Just because you come in late doesn't mean you get to have your own conversation. If you wanted to have that conversation and not have it part of our video notes, then you should have gotten here on time to have that conversation before being in our video notes. All right. In other words, our angle bisector is equidistant from each side of the angle. Remember, equidistant just means equal distant. So congruently, the same measure away from something, from the side. So it says to sketch the angle bisector in the angle below. So just a quick review of using a protractor, because we're going to need to be able to do that. I thought I had a protractor up here, but perhaps I don't. Yes, I do. All right. Review of using the protractor. Remember, also, the earlier you get here, the better you have of picking a good protractor. The center, or the bottom line, needs to line up with one of the two rays. And then the 90 degree that comes out, that intersection there needs to just be lined up with the corner. Once you have everything lined up, then you can see how big the angle is. You're going to have two choices. You're going to have two numbers. I have 50 degrees. I have 130 degrees. 50. How do we know it's a 50 and not the 130? Because of where the 0 on the bottom is, right? So we always want to, if I lined up here, you look and see where the 0 is, and that's how much we're opening. We're opening 10, 20, 30, 40. We open a total of 50 degrees when we open up, okay? So if I want to bisect 50 degrees, where do I want to put my bisector? How many degrees? 25. So 25 is going to be right here. 25 degrees. This is my bisector. So this is the angle bisector. Dividing that angle into two equal halves where each side is 25 degrees. So that the whole thing is 50 degrees. Notice I put little matching arcs on them because that indicates that they have the same measure. Okay? The angle bisector, it's real tempting to say it's in the middle, but it's not the same as a midpoint because it takes all those points to divide it in half, right? You need the whole angle bisector to be able to divide the whole angle in half because angles are infinite. They go on forever, the rays. But each point on the angle bisector is equidistant to the side. Okay, so for example, if I just randomly pick a point somewhere on my angle bisector, remember distance is perpendicular distance, so if I want to leave this point and figure out how far it is from this line, I would have to make a 90 degree angle at this line. So if you want to do it with your eyeball and just kind of sketch it, you can. If you want to measure it and make sure it's correct, you're going to line up the protractor, the 0 to 0, with that ray. And then you want this line that says 90 to intersect that point that you drew. So you just slide it over. This is like what we did last Thursday. Once you have it lined up with the ray, and you have this one lined up to the dot and the 90, then you can put your pencil down at the 90 and the outside, but don't actually draw the line because we just want the distance from the point to the ray. So then I line up, and I just want to measure from the point to the ray. Okay? If you have a random sheet of paper and you want to make that a little bit easier for yourself, okay? Remember, most of our paper, actually I don't know about this one because I cut this one by hand, but most paper has a 90 degree angle in the corner. So you can also just use a sheet of paper and just slide it over until you hit that point and then go, oh, look, there's 90. That's a 90-degree angle there. And then you can make your line this way. That makes your life a little easier, then you can do that as well. Okay? So this point is equidistant to each side. So these distances will be, if we measured correctly, now remember, notice I didn't even bother using a protractor for the second one, so this piece of paper I cut with scissors. So it may not have really been a 90-degree angle, but we can see how close it was to a 90-degree angle. If I measure, that is almost 2 centimeters, not quite. It's like 1.8. And if I measure this one, it is almost 2 centimeters. This one's a little closer to 1.9, so that must not be a perfect square on that corner. Okay? Every place along this line that I put a point, I'm going to end up with that same situation happening. So if I pick a different point on this line, if I come out here, and I were to do the same thing, I don't know if I have anything perfectly square. I'll just post it from last week. And I were to do the same process, line it up, make a 90. This length is going to be the exact same length as if I do the same thing on this end. Yeah, I would. That way you can see both of them. You have at least 2 examples. So you can either use your protractor and measure it, or if you have a little square piece of paper, you can do that too. Okay? It should be the same measurement. And the lines that come out that go perpendicular to the side, they're always going to be parallel to each other, because if you think about 90 and 90, right, those are consecutive inside angles, and so if they are supplementary, then the lines are parallel. Or up here, I drew them as corresponding angles. If corresponding angles are congruent, then the lines are parallel. So your distances will always run parallel to each other. Okay? So far, so good? Okay, let's practice doing a whole bunch of these, because they're fun. Yay! All right, so here I have my sheet that we've been working on, right? We did altitudes, and we saw our altitudes, depending on our triangle, our altitudes are either inside a acute triangle, they're at the right angle of a right triangle, and they are outside. The intersection is outside, and it's called the orthocenter. For my medians, the centroid is the centrist center of all the centers, and it's always inside. It's the balancing point of that triangle. And remember, the very long from the vertex to the center is twice as long as from the short side from the side to the centroid. And now on the back, we're going to do angle bisectors. So for my angle bisectors, I'm going to line my protractor up with the bottom of the triangle and slide it to the left so I can see how big the angle is. It looks like it's about 75 degrees to me. What is half of 75? 34. 37.5? 37.5. So that's 35, 36, 37, about halfway in between, right about there. This is the first one we're looking at where it doesn't have to be a distance. So we get to actually draw it as a ray. Each of these are both 37.5. I'm going to mark them as congruent. Then I'm going to turn my paper sideways. And I'm going to do the same thing. I'm going to line my protractor up at the bottom, slide it over to the left. And that one is about 66 degrees, so half of 66 is going to be 33 degrees. 30 degrees is here, 31, 32, 33 is right about there. So this side here is the same as this side here. Notice they weren't the same degree, so I put double arcs on the second angles to show that they're the same as each other, but not the same as these. Okay? You can do the third angle, but do you think you have to? No, because what's going to happen?
Go sneeze.
Yeah, it's got to go through that same intersection. So if you want to skip the measuring part, you could just sketch it in. And then you could check and see how well you did and check to see the measure of them. That whole angle is almost 40, so then it goes right about through the 20. So that's pretty close. 40 degrees, half of 40 is 20. Good on us. Again, that's a different angle measure from these sets, so I'm going to do 3 arcs to show that they equal each other, but they don't equal the other 2 sets. So far, so good?
Yes.
Okay. My right triangle, I'm just going to line up on the hypotenuse and then slide over to the left. That is about 27-ish. Did you say 30? It's like 27. Half of 27 is going to be 13.5. 5, 10, 11, 12, 13.5 is going to be right about there. The right angle is easy. We already know how big it is. How big is the right angle? 90 degrees.
That was hard.
So half of that is going to be 45. So I'm going to measure that one next and just do my 45 degrees. 45 is right here. And again, I don't have to measure the third one because I know where it's going to fall. It's going to intersect right along the intersection I've already made. One, 2, 3. 1, 2, 3. And if I want, I could measure it to just kind of see how I did. And that is about 63 degrees. So half of 63 would be 16.5. No, 30.5. 31.5 is where it looked like I ended up. Okay. Pretty close. Alright, and then my obtuse triangle. Let's start over here on the left. That is about 21, so a little more than 10. 10.5. The protractor's not long enough. This side is the same as that side. I'm just going to come to the left since I've got myself here. And that's 110 degrees, so half of 110 degrees is 55 degrees. Notice I'm using my outside numbers this side because I slid to the left.
Yeah, because we're smart.
To the left, to the left. Different size angles, so different arcs. And then again, I don't have to measure the third one. Once I have 2, I know where the third one's going to go. Right through there. The intersection of the angle bisectors is called the in-center. Anybody want to know why?
In the center.
Well, they're all centers. Our centroid is in the center. In fact, I'd say the centroid is the center of all the centers.
Well,
This one is called the in-center because it is the center of a circle that is inscribed inside the circle. What we mean when we say inscribed, it means all the sides of the triangle are touched by the circle. Let me show you what I mean. If you want to borrow a compass when we're done because you want to do this to your picture, you can. I'm just going to make you take an oath that you promise not to poke somebody, including yourself, with the dangerous pointy object. If I put the dangerous pointy object on my in-center, I'll be able to see how well I drew this, because when I draw a circle, it should touch each side in one place. Okay. I did pretty good on that one. This one, oh, I didn't do near as good on this one, I don't think. Oh, maybe. Not too bad. A little off to the right over here. And then my last one. I didn't open my compass wide enough. There we go. Touches each corner in one spot. Okay? What that means is that center, called the in-center, is equidistant to each side of our triangle. Okay? So what that's going to look like when we say it's equidistant to each side of the triangle, okay, that's going to mean if I were to draw the radius in to the side where it touches the edge, that radius, it's going to be perpendicular to the side, because that's how we measure distance, is perpendicular. It's going to be perpendicular to the side, and that distance, since it's the radius of a circle, is going to be equal every single time. Because they're all the radii. Does that make sense? Okay. So, the distance on the green, on the angle bisector, they don't have any, there's nothing we know about them. None of them are necessarily equal or 2/3 like they were last time, or twice as long. But if you have that circle drawn in, or you have the perpendicular distances drawn in, all those perpendicular distances are equal. All the perpendicular distances are equal. Okay, so if you want, you could sketch in here the triangle that would fit in here. Usually I kind of make it a little dotted, and then I just kind of try to make it look as circular as I possibly can. If you want to do it later with an actual compass, you are more than welcome to borrow one. So the distance where we touch at a 90, the distance where we touch at a 90, and the distance where we touch at a 90, those will all be equal. Okay? They will all be equal. And that's what it tells you on the next page. The in-center is always inside the triangle, and it is the center of the circle inside the triangle. So if I were to sketch a triangle in each one of these, it's the center of the circle that fits perfectly inside each one. That last one's not very circular. Pretend it is. Okay? The perpendicular distance from the in-center to each side is equal. Is equal. The perpendicular distance, which is how we always measure distance, is equal. Alright, so my first example here says, name an angle bisector in the figure below. So where do I see an angle that's been divided in half? At angle A, I can see this angle here and this angle here are both the same. So how do we name that angle bisector? Right, segment AD, because it doesn't have an arrow on the end, so it's a segment AD. So we already looked at this picture. We've already said that BE, we know, was a median. We know that CF was an altitude. And now we know that AD is an angle bisector. So the only thing left is what we're going to do tomorrow, which is going to have to be BG, because that's the only one left we haven't looked at, right? All right. Then we have this picture again. This is the third time we've seen this exact same picture, but today it's going to get a whole new property. Because on Thursday we said if WY is an altitude, we knew we had right angles, right? Then Friday we said if WY is a median, so we knew we had a midpoint. Today, WY is an angle bisector. So today we know we have congruent what? Angles, right? We know that this segment here is dividing the angle that it intersects, or intercepts, really, into two equal halves. Now I can't say angle Y is congruent to angle Y, which it is, but that would mean it's the same exact angle. How do I name these two angles separately? How can I name the top angle so I know it's different from the bottom angle?
Angle WYZ.
Angle WYX, or what?
WYZ.
Well, if I wanted to name the top one, what are the two options for the top one? Yeah, either XYW or WYX. I'll do it WYX because that's the first way y'all said it. Is congruent to, now name the bottom one. WY what? Z. Or ZYW, right? That's all we know about that picture. We know nothing else. Well, we know that WY is reflexive, so it's equal to itself. We always know reflexive sides are equal. All right. My next set, it says each triangle has an angle bisector or an in-center shown. Find the measure of angle HSD if the measure of angle 1 is 21.5. So if angle 1 is 21.5, what else do we know? Angle 2 is 21.5. But let's see what it wants me to find. It wants HSD. HSD. So it wants the whole thing, which is going to be how much? 23?
41.
Let's go with 43. The measure of angle HSD is going to be, since I know this angle, I know it's going to be twice as big as the one side, right? So it's going to be 2 times 21.5, which is 43 degrees. Okay. The next one, this time it says find the measure of angle 1. Found it. It's right there. Done. I'm just kidding. If the measure of angle BTL is 48 degrees, BTL, that whole angle is 48 degrees. So I know the measure of angle BTL is going to be twice as much as that angle 1, right? Measure of angle BTL is 48. That's going to be 2 times the measure of angle 1. So how do we get rid of the 2? Yeah, just divide in half. And you can do that in your head, right? You don't need to, you probably didn't need to write that out. How big is the measure of angle 1? 24 degrees. There are going to be times you're going to want to be able to do that math behind it, though, because you may end up with something. Where did I do it?
That's 48
You might end up with a picture that looks like this. And so you have two options. You can either say it takes two of these to equal this, or you can say this is equal to half of that. So notice I wrote it in those two different ways. The 7x plus 2 is equal to half the whole thing, or it takes two 7x plus 2's to equal this whole thing. So it's important to be able to put it in an equation for when you have expressions instead of just numbers. Does that make sense?
Yes.
Okay. All right, glad I had that handy. All right, the last one on this row, we still have two more after it, but the last one on this row, I know I've got an angle bisector, right? And so I have an in-center, so C is my in-center. And I can see they've drawn in those perpendicular distances. And so I know, what do I know is the relationship between these orange segments? They're all the radii of that circle that's inside, so they're all equal to each other. This is equal to this is equal to this. If C to G is 18, find C to Q. How long is C to Q? 18.
What is it called, the radius?
Yes, because remember this is the center of the circle that fits perfectly inside, right? And that's what we call the distance from the center to the side, is the radius. So there's the circle. I just sketched it. Not the most beautiful circle I've ever drawn, but not the worst either. Exhibit A right there. It's pretty terrible. But not the worst. Not the best. All right. Next. CA equals 8. So if CA equals 8, that means CE equals 8 and CT equals 8. All of those equal 8. Okay. AJ equals 15. AJ equals 15. Now, that doesn't tell me anything about anything else because I don't have necessarily midpoints. I haven't said anything about anything else. So really, that's all we know. AJ is 15. There's nothing else I know from that. Find CJ. CJ. This is the piece I'm trying to find. Any ideas? Yes. Pythagorean theorem. CJ is just the hypotenuse in a right triangle where my two legs are 8 and 15. Remember, your right angle points to the hypotenuse, so I can tell I'm trying to find that hypotenuse, CJ. So a squared plus b squared, 8 squared, plus 15 squared, equals whatever CJ is, squared. 8 times 8?
64.
15 times 15? It is 225 equals CJ squared. 64 plus 225? 289 equals CJ squared. I don't want CJ squared. How do I get rid of the square? Square root, which in Algebra 2 they tell us means positive and negative, but since we're a length, we get to just do the positive. What is the square root of 289?
17.
So that's how long CJ is. That doesn't tell me how long anything else is. All I know is CJ is 17. I don't know how long NC is. I don't know how long CF is. I only know CJ. Make sense? Okay. The last one is almost the same, but not quite as what we just did. So when I look at the last one, CQ is 3. Uh-oh. Which means what else is 3?
Times all the other radius.
All the other radii, which are all the other ones that go to the 90-degree angle, which are going to be CN and CI. This one's going to be 3. And this one's going to be 3. Those are the only things that are equivalent when you have an incenter, is the perpendicular sides. Nothing else is equal. Okay? All right, then CE is 10. So this piece here is 10. I don't know how long nothing else now has to be 10. That's the only one that has to be 10. And last but not least, it says to find EN, this piece here. Okay? This is not exactly the same as the last one. You know why? Can you tell why?
I'm not finding the hypotenuse.
Yeah, I'm not finding the hypotenuse on this one. My hypotenuse, I know it. My hypotenuse is 10. Because it's the one across from the right angle, right? And so on this one, I'm trying to find one of the legs, right? So on this one, I'm trying to find one of the legs. So instead of a squared plus b squared equals c squared, where I don't know the c squared, this time, I don't know this en. Plus the other leg is 3 squared. That's going to equal my hypotenuse, 10 squared. So en squared plus 9 is going to equal 100. So en squared is going to equal, when I take the 9 to the other side and subtract it on both sides, subtraction property of equality, what am I left with? 91. How do I get rid of the square on en? Square root. 91 doesn't square, so that's okay. That just means that my answer is en is the square root of 91, which is not simplifiable. You could make it into a decimal if you really wanted to know how long it was. Approximately, right? But this is an exact answer, so it's nice to leave it as exact as you can. En is the square root of 91 degrees, which is going to be somewhere between 9 and 10. Somewhere in there. Okay? Questions? All right. If there are no questions, then your assignment is in Schoology.